So I'm sharing my screen. Is it visible?
Yeah.
Great.
Yes. Alina, could you please send me the link to the board?
Yeah, just a moment.
Okay.
I sent you link so you can post in Slack.
Okay, thank you.
So we can start after 4 minutes.
Sure. We will wait for 4 or 5 minutes and then we will start.
Yeah, okay.
So it is already 4 o'clock, so let's start. Hi, everyone. Thank you for joining us today. My name is Alex. I am a Kaggle competition master and research engineer that working with object detection and tracking systems for 3 years. I'm broadcasting to you from Kyiv, Ukraine, and I hope that you will enjoy this lecture about deep learning for object detection from the safety of your homes. Our agenda for today's lecture is following. First of all, we will start from object detection fundamentals that essential for understanding any publication on object detection. After that, we'll move to basic approaches for deep learning based object detection. Then we will review how we can modify these object detection systems to get the best trait accuracy, to get the best speed accuracy trade-offs that's suitable for our tasks. Then we will review common object detection libraries that used to build object detection pipelines. And in the end, we will review common object detection approaches that used for processing video data. And just before we start, I want to put some slide conventions. First of all, this lecture will cover only a high level concepts. So if you want to learn more about some cool stuff and to dig deep in this into ideas, I recommend you to use QR codes that I put in the left bottom corner of the slides, or simply to use this hyperlink when the presentation will be published in the Slack channel. Also, there is a slide number which you can use during Q&A session if you have some questions to concrete slide. So we will start with object detection fundamentals. Let's recap that image classification task is a task when we need to assign a label from a predefined set of labels to the image, which describe which categories are depicted on the image. Object detection extends this task when you need not only define which categories are depicted on the image, but also where they are located on the image by predicting top left and bottom right corner of minimal and closing bounding box that fully covers our objects. Object detection is unfortunately not a standalone task. And generally, we can see object detection as a part of complex applications. So let's review some of them. As instance is Tesla Autopilot, which uses the input from object detection systems to detect cars, pedestrians, and signs, and to use this information to predict the behavior of the car on the road. Or for instance, Amazon Go stores, where we need to detect customers and to detect which products took by these customers to properly charge for them. Or simply detect face to unlock your phone. As we can see, all this application has their own set of limitations and their own set of challenges. So let's try to classify them. And generally, any object detection system facing these 5 core challenges, first of all, we need to detect objects at different contexts that should at different illumination and from different points of views. This 3 task is pretty common for any computer vision task, But when we are trying to do object detection, there is additional task which is specific for object detection, like detecting of objects of different size, like this person that's close, which close to camera, and this one that's pretty far from camera. These two persons are considered as equal and have equal weight for our object detection system. And also we need to properly detect occluded objects, which means that we must precisely localize our objects even when they are pretty heavily occluded by other objects or by some background stuff. To properly handle all these challenges, we need a lot of data. So let's review most popular object detection data sets. And one of the oldest data sets that's available today is Pascal WOC. WOC standing for Visual Object Classes. It was released in 2005. And nowadays it consists 20,000 images on which annotated 20 categories. As we can see from image samples, this dataset consists generally from the simple scenes on which we can see only several objects, which generally from the same category. So among object detection researchers, Pascal WOC dataset are considered as some type of MNIST dataset, which we all familiar from image classification task. So when first deep learning object detection approaches was released, this dataset was quickly beaten. So research community start looking forward for new, more challenging datasets. And such challenging dataset become MS-COCO. MS stands for Microsoft and COCO for Common Objects in the Context. It was released in 2014 and contained 120,000 images on which annotated 80 categories. As we can see from image samples, the scenes are pretty complex. They contain several objects from different categories. Also, this dataset contains not only object detection annotation, but also instance segmentation annotation and semantic segmentation annotation, which can be used to build more robust object detection system. For today, most of new object detection approaches are evaluated on a MS-COCO dataset, and researchers are reporting their results on this dataset. And release of MS-COCO was a huge step towards to creating large-scale object detection dataset, but its size is pretty small compared to ImageNet's 14 million images. So to close this gap, in 2016, Google released Open Images dataset, which contains 1.8 million images on which annotated 600 categories. To annotate such a massive dataset, Google engineers used machine-assisted annotation techniques, which including annotation of images by the best Google's algorithms, and then human annotators then only selected valid annotation, which resulted in a large amount of misannotation in this data set, like this person, which not annotated by machine, and hence Open Images does not contain annotation for this object. So Open Images is not pretty famous in object detection community because not all images contain annotation for all objects. but some researchers that developed algorithms that robust to noise in annotation and robust to missed annotation heavily utilize this data set to build their solution. And the last data set, which I will tell you, is object detection objects 365. It was released by McVie company in at CVPR 2019, and in March 2020 received massive update, which extend dataset to 2 million of annotated images, on which fully annotated 365 categories, which makes this dataset the biggest object detection dataset, which open sourced. And the only drawback of this dataset is the license. So this dataset is released under academic purpose only license, which limits usage of the data from Objects 365 dataset for creating commercial and non-commercial applications. Okay, and let's discuss the most important thing in any computer vision task is the metric, which used to decide whatever your algorithm is good or bad. And to calculate object detection metric, first of all, we need to match our predicted bounding boxes with ground truth bounding boxes. This is done by calculating intersection over union metric, or IU, which simply divides overlapping area of your predicted bounding box and ground truth bounding box by their overlapping area. Such simple metrics help us to incorporate information about both relative position of the bounding boxes and their sizes into a single value. And as we can see, this value ranges from 0, which corresponds to bounding boxes that not overlapping at all, to 1, which corresponds to fully matched bounding boxes. In research community, there is agreement that if two bounding boxes has overlap greater than 0.5, we consider it that this is pretty the same bounding boxes with some moderate error, and we consider these two bounding boxes as matched. So now when we know how to match our prediction to ground truth, we may calculate one of the most popular object detection metric, which called mean average precision at IU 0.5. It calculated in the following way. First of all, we need to match all our predictions to all ground truths, and all predictions that have IU with ground truth, with any ground truth higher than 0.5, we consider this ground truth as true positives. Otherwise, we consider these predictions as false positives. And then using these true positives and false positive values, we may calculate two of the most popular metrics is precision and recall. And then using confidence of predictions, we may arrange this precision and recall metrics into precision recall curve, and then calculate average precision of each prediction, which is simply area under this precision recall curve. And this is how average precision metric calculated. If we have several classes in our data set, we repeat this procedure for each class separately, and then simply averaging them. This is how mean average precision metric calculated. So mean average precision metric is pretty good. It's pretty simple. It's simple to calculate and simple to understand. But the problem of this metric is that mean average precision not telling us anything about the localization quality of our model. And generally, we want that model with higher localization capabilities have the higher score. So alongside with COCO dataset was released novel metric. I will refer to this metric as COCO metric for simplicity. And it calculated simply by averaging mean average precision for 10 different thresholds, starting from 0.5 to 0.95, step 0.05. So in this metric, the predictions with the higher localization with higher localization score is contribute to our metric more, and hence the model with the higher localization capabilities will have the higher score, which actually push researchers to search for more accurate models. And as we can see, this metric is quite hard to improve. As a result, we can see that datasets that use COCO metric is having lower average precision scores compared to the datasets that use simple mean average precision at IU 0.5. So I hope this table will help you to understand which scores are considered as good results on which dataset, and you can judge models from different datasets and understand whatever they are good or not. Okay, now when we're familiar with object detection fundamentals, let's move on and review how deep learning object detection models are emerged. And we will start from the one of the most popular deep learning based object detection, which object detectors, which called RCNN. And it consists from two simple steps. First of all, we applying selective search algorithm, which clusterize each pixel on the image and merge these pixels into a group of similar pixels, which form such zones, which we called regions of interest, or ROI for short. And then we select 2000 ROIs from different stages. And then we simply apply, put these regions through the convolutional neural network, extract some deep features, and use these features to classify these regions. As a result, we may detect the objects. As we can see, the ROIs that predicted by selective search algorithm may not well cover the object. So authors introduced additional bounding box regression head, which learn how to slightly adjust these bounding boxes to get better IU score at evaluation stage. So as we can see, this simple approach beaten one of the most stronger classical object detection model, which called DPM, deformable part models, by 13% margin. And RCNN opened a new page, a deep learning page at object detection history. So despite the good result, RCNN has one major drawback. The full computation of RCNN approach on the one image took approximately 1 minute, which a lot. So researchers start looking for ways to speed up this approach. And lately in 2015, the faster version of RCNN was introduced to public. It called Fast RCNN. And based on a simple calculation, if we do a little math, we can see that instead of computing deep learning features from our ROI regions 2000 times, we may simply to run our image through the network one time and then crop these regions and try to classify them using our classifier network. In theory, this approach could speed up our model by 10 times, but here's the problem. Our classification network consists from two fully connected layers, which accept only a fixed shape features. So we need to find a way to transform our arbitrary sized regions into a fixed shape, into a fixed shape regions. So here, so this is the place when the famous Roy pooling algorithm step in. Assume that we want to transform this 7 by 5 size region into 2 by 2 region. So we can do this by simply splitting this huge region into several almost equal by size regions, and then simply applying max pooling algorithm at these regions to get the fixed shape values. So I want to highlight that both max pooling and splitting algorithm are fully differentiable. So when we incorporating this Roy pooling algorithm in our network, we can train all this architecture in end-to-end fashion and hence improving both speed and quality of our model. So even after improving our algorithm, so after speed upping our algorithm by 10 times, it's still quite slow compared to classical computer vision object detection rivals. So authors start looking forward to improve the speed of fast RCNN algorithm. And lately in 2015 was introduced faster RCNN, which improved version of fast RCNN. And now researchers simply profiled all algorithm of fast RCNN and discovered that the selective search algorithm that we used starting from RCNN was the bottleneck of the whole system, and deep learning part was much faster compared to this iterative algorithm. So they decided, so when we incorporate this selective search algorithm into our network, we can greatly speed up the whole pipeline. So they come up with following architecture. We run our convolutional neural network we process our image by convolutional neural network and getting some features. Then we use these features to generate our proposals by subnetwork, which they called regional proposal network, or RPN for short. And then we use these proposal regions to crop these features and then to classify them by the second stage. So let's review how this regional proposal network works. And it was built on one but powerful idea. So imagine that we are sliding our feature map by such sliding window, and imagine that the center of this window are lying at this feature cell. So we may use features from this feature cell to predict whatever this sliding window is containing some object or not. And then by simply sliding this window across all the feature map, we may localize all the objects that are located on our image. Obviously that not all of our objects will perfectly fit into a such square region. So authors come up with a bunch of sliding windows of different sizes and different shapes, which nowadays are known as anchor boxes. And the pipeline is following. We simply using convolutional neural network to predict whatever these regions and whatever in these regions and in these anchor boxes are containing some objects or not. And similar to RCNN-HEAD, we additionally predict regression coordinates to better cover all the all distribution of bounding boxes in our dataset. And hence, by incorporating this RPN algorithm into our RCNN approach, we may increase both speed and the quality of our model. Lately, in 2016, when researchers start to looking deep into the results of RPN, they found that the quality of ROIs that produced by RPN is pretty good, and they even can be used as a reference for the objects. So they come up with following idea: what if instead of predicting simply whatever this region containing some object or not, we may predict which class are containing this concrete region. And then we can simply get rid of this ROI pooling algorithm and classifier and speed up overall our pipeline. So following this simple idea, in 2016 was released single shot multi-box detector, or SSD for short. It's apply RPN algorithm at different stages of VGG network, and hence directly predicting location and classes of all the objects on the image. SSD showed pretty good results in terms of speed, and generally SSD is the first deep learning based object detector model that can run in real time while maintaining the same or even better performance compared to faster RCNN. So release of SSD introduced a new family of object detectors, and nowadays we are dividing all object detection approaches into two categories. First one is called two-stage detectors. This is the family of detectors in which we at first stage predicts ROI possible locations of the objects, and then we simply classify this ROI at the second stage. The most popular representatives of this family is RCNN, fast RCNN, and faster RCNN. And on the other hand, one-stage detectors are performing both localization and classification of our objects at single stage. And one of the most popular representatives of one-stage detectors is SSD. All right. Now, when we're familiar with basics of object detection approaches, we will review the enhanced and we will start with SoftNMS. So during evaluation section, I omitted the topic of duplicated detections for simplicity, but generally during evaluation, if we have several predictions that assign it to overlapping IU. So as we can see on this image, assumes that we have two predictions of two horses that staying close one to each other. And when we simply apply NMS algorithm, the second horse, which have lower confidence score, will simply disappear. But as we all understand, this is a pretty good detection. And if we find some way to not to remove this prediction, but to say, reduce the score of this prediction, we may come up with much better post-processing algorithm. And this idea was incorporated in SoftNMS, which instead of removing this bounding box, which is simply assigning 0 score to this bounding box, we may simply decrease the score of this prediction by amount of overlapping area with the higher confidence bounding box. So literally by changing one line of code in NMS, we can improve results on a COCO data set by 1% without any overhead during inference phase. Okay, second one idea is called ROI align, which is improved version of ROI pooling. So generally, ROI pooling has one major drawback. It's working only for integer-based ROIs. So assume that we have ROI, which located in non-integer coordinates. Then ROI pooling is simply rounded these coordinates to the nearest integer and pool the smaller region of features. Obviously, we are losing information from our ROI region, which decrease the performance of our classifier and decrease the localization capabilities of our model. So to overcome this issue was proposed a simple idea. There is always exist some feature grid in which this concrete ROI is lying in the integer coordinates. So simply by switching from the origin feature grid to this perfect feature grid, which depicted in the blue dots, we may solve this problem of pulling from integer coordinates, and we will pull the full set of features that corresponds to this concrete region. So we can simply switch from origin grid to this perfect grid by simply interpolating values of this perfect grid from the nearest values of origin grid by applying bilinear interpolation algorithm. So as we all understand, this simple approach creates a little overhead over an origin ROI pooling algorithm, while improving our two-stage detectors by 6% on COCO dataset. Okay, let's move on to next idea, and this is feature pyramid network, or RPN for short. It can be incorporated in both one-stage and two-stage detectors, and it's used to increase the performance of our model for detecting small objects. By design, all our neural networks processing images by chaining convolution operations and forming a set of feature maps of different spatial size and with different feature quality. So generally in object detection, we are using high-level feature maps which contain semantically fine features which are suitable for object classification and which suitable for detecting large objects like humans, vehicles, ships, etc. But when we want to detect small objects like TV control or cups or, I don't know, balls, it's pretty hard to use such low resolution feature maps because information about these small objects are lost in these intermediate layers, which are not suitable for well classifying foreground objects and to distinguish between foreground objects and background objects. So authors come up with the idea of enhancing these low-level feature maps using semantically strong high-level feature maps. So we can do this by simply scaling up by linear interpolation our high-level feature maps, and then additively aggregating our high-level feature map with low-level ones, and hence semantically enhancing the features as these low-level feature maps, and then using this feature pyramid for predicting our objects. FPN is adding a moderate overhead to modern object detection models, while increasing their performance by 2% on COCO dataset. And this 2% mostly come from detecting small objects that are smaller than 32 by 32 pixels. Okay, the next idea is called focal loss. It can be incorporated in both one-stage and two-stage detectors, but mostly focal loss is utilized by one-stage detectors to prevent foreground and background class disbalances. So the idea behind focal loss is following. All images contain only a small fraction of ROIs that really containing some object, and the vast majority of our ROIs generated by RPN is containing some background regions which are easily classified by our detector. And when we are calculating loss for such regions using binary cross entropy loss, which depicted in blue in this plot, the loss scores of such regions is lying somewhere here in well-classified region. But when we are trying to apply our optimization algorithm like SGD or ADAM, such vast majority of easy to classified regions starting to overwhelm in the optimization process. And for our optimizer, it is much easier to simply push these easy to classify regions even further by simply increasing their scores, instead of dealing with these hard to classify samples, which are really contributing towards to creating robust and good object detection models. So authors added a simple weight coefficient into cross entropy loss, which downweight the contribution of such well-classified examples to our loss, and hence making optimizer to concentrate more on these hard samples. We may control the strength of this downweight process by varying gamma, and they empirically showed that gamma of 2 is the best choice for object detection systems. And as we can see, by simply incorporating focal loss into one-stage detector, we can improve the quality of detector by 4% on COCO dataset without introducing any additional computation at inference time. Let's move on to next idea, and this is my favorite one. It calls deformable convolutional network, or DCN. It can be incorporated in any backbone for both one-stage and two-stage detectors, and based on a simple observation. When we are pulling features using our standard convolution, we are pulling from a squared region, which which we already know that not suits for every objects. Such square pooling regions may contain may contain huge amount of context information, which decrease the performance of our classification algorithm and may result in overfitting of our object detection model. So authors come up with following idea: what if instead of pulling from such square regions, we will pull from arbitrary sized point clouds, and we will give the network a tool set for predicting which shape must be in our pooling region, and network will adapt to pull the best features which suits the best for detecting objects on this concrete image. In practice, it can be done by applying following algorithm. First of all, we are using input feature map to generate so-called offset field, which is used to simply offset our pooling points from the convenient convolution pooling field, and to form such a pooling point cloud, and then simply pull features from this point cloud and to form new output feature map. Obviously that such operation is computational heavy, and this operation is not well optimized by the hardware. So authors come up with following idea: what if instead of applying directly such instead of applying pulling from this point cloud, we may simply use these offsets to rearrange input feature map in the way that when we will pulling by a convenient convolutional layer, we will pull from this point cloud, and such way of implementing this deformable convolution layer will be well optimized by underlying hardware and will create only a moderate overhead over classical convolutional layers, and obviously will increase performance of our model. And on Coco dataset, adding deformable convolution increase performance of models by 3%. Okay, let's move on to more complex stuff. And we will now learn about CenterNet, one of the most popular anchor-free one-stage approaches. So idea of anchors are extremely powerful, and mostly all object detectors are using anchors to predict ROIs and then to classify them. But what will happen if we receive some object which not well covered by our predefined anchors? Well, our network will simply not detect this object, which is not a desirable behavior for any object detection system. So authors proposed instead of hard coding and a set of anchors to simply predict the shape of the object from the input data. So they're doing this in the following way. First of all, we processing our image by hourglass network, which compress and decompress our feature map, and hence creating deep and rich high resolution feature maps, which we then use to predict the corners, top left and bottom right corner of all the objects on the image. And then we can simply try to combine all these corners and to form all the possible bounding boxes. As we understand, the amount of such bounded boxes is high. So instead of doing such a brute force, they introduced additional embeddings branch, which predicts embeddings features for all of these corners, and then we are trying to use these embeddings to match the corners from the same object and to form a limited set of objects on the image. As we can see, not all of these bounded boxes are really well covered objects. So additionally, authors introduced so-called center heat map, where they predict the centers of the objects which depicted on the image. And then they use the simple idea that predicted centers must lie somewhere in the center of the bounded box. So using this simple idea, we may simply suppress the bounded boxes that not well cover objects or that predict object or simply suppressed false positives that predicted by corner branch. As we can see, while maintaining the same level of performance, CornerNet outperform convenient anchor-based approaches by a small margin. But using CornerNet, we can detect objects that lies far away from a distribution of objects from the train set, which generally making our models more robust to distribution of data. But this approach, but researchers still struggle to build good anchor-free approach that are not based on such deep neural networks like Hourglass 104. And we simply cannot use CenterNet with some shallow network with such as MobileNet or SqueezeNet because CenterNet simply underperform convenient object detection models that are based that are using ideas of anchors. But recently was introduced some hybrid approach which incorporated both anchor-free and anchor-based approaches into a single algorithm. So let's review how it works. So first of all, we are using our predicted feature maps to predict where lying the centers of our objects and to directly regress approximate width and height of our object. And then using this information, we may dynamically generate anchors for each position in our feature maps. And then we may use these dynamically generated anchors in our RPN algorithm to classify them and to adjust their location. But before we can use these anchors, we need to solve one principal problem. The feature distribution in this feature map are misaligned with these anchors because we are dynamically generating these anchors in the runtime. So we need to do something to align distribution of anchors and the distribution of underlying features. To do so, authors proposed simple idea. Let's we use the predicted shapes of our anchors, and using this information, we may generate an offsets for our deformable convolutions, and then use these offsets to adjust our feature map to be well to be well aligned with generated anchors. So by simply incorporating this guided anchoring RPN, or GARPN for short, we may increase the performance of our model by 2% on COCO dataset without introducing any heavy computational components into our network. Okay, and the last idea is called Cascade RCNN. It actually was developed more like a way to hack COCO metric, but Cascade RCNN produced pretty good predictions that are well localizing all the objects on the image. So let's review how authors come up to this idea. And they started from simply reviewing the distribution quality of bounded boxes predicted by RPN algorithm and the bounded boxes predicted by RCN. And as we can see from this distribution, after RPN stage of our RCNN algorithm, only 3% of our predictions has IU higher than 0.7. And after simply applying RCNN hat one time, we increase this number to 17%. So authors come up with a pretty simple idea. Let's try to apply RCNN hat several times. So they reused boxes predicted by first RCNN hat as a new ROIs. Then they pull features for these predictions and then try to adjust the localization and the confidence scores of these predictions. And they repeat this procedure 3 times. And as a result, then they increase the localization. They improve the localization quality of predictions produced by Cascade RCNN. And as we remember, the model that has higher localization capabilities has higher COCO metric. So as we can see, this simple idea improves COCO metric by 4%. While introducing moderate computational burden over classical fast RCNN approach. Good. Now let's switch a little bit from theory to practice, and I want to start practice with telling you that building object detection pipeline, it's quite a handful job. It contains a lot of engineering stuff where you need to implement matching algorithm, balancing algorithm, selecting algorithms, and so on, which raised the entrance threshold for object detection to extreme heights. And object detection is one of the most complicated topics in all computer vision. So object detection wasn't popular until publishing of some open source object detection libraries that handle all this underlying engineering stuff instead of us. And nowadays, when we are talking about using some object detection library, we are generally selecting from these two libraries. It's actually we selecting among TensorFlow object detection API and MM detection, or simply we selecting between TensorFlow and PyTorch. So let's quickly review these two libraries. And we will start from TensorFlow Object Detection API, which was released by Google research team in July 2017. it was actually released as a code base for publication of one research team in Google, and they fastly incorporated this this code base into their research pipeline, and nowadays they are using this TensorFlow object detection API to build their object detection systems. TensorFlow object detection API was updated several times, and the recent update was on July 10th of this year, when they introduced support of TensorFlow 2.0 for the long support for 3 years of existence of this library. They simply come up with a huge amount of legacy code that's hard to understand, and multiplying this but bad code architecture, we will come up with some libraries that hard to understand even for deep learning, even for object detection specialists. So generally, newbies are liking to use MM detection, which was written in PyTorch and released in early 2019. It has good crystal clean architecture from day zero, and multiplying this but well-documented code, this library starts fastly to gain popularity among object detection researchers, which start to contribute into this library and start to publish their new ideas into and merge their code base into this library. So nowadays, MM detection is the biggest object detection library, which contain all the cool stuff which we can find for object detection, including all these ideas which I talked you about. So let's review. Let's do a little bit of coding and review how we can define our object detection model using a tool set of MM detection. So I already done my homework and I created my custom model using MM detection toolset. So let's make a quick look for in this config, and I will highlight the essential parts of this model. First of all, we start from defining the architecture of our model. I selected Cascade RCNN as the best approach for with good localization capabilities, and I based my Cascade RCNN on a batch normalized ResNext, which has deeps of 101, 32 groups, and base widths of 4. I additionally frozen first 2 stages of ResNext to prevent gradient calculation in these first 2 stages, where we have a high resolution feature maps, and hence saving a little bit of memory to fit this model into 8 GB limit. And additionally, I added deformable convolutions into my ResNext, and I added these deformable convolutions only for the light stage to not add a lot of additional computation over ResNext. As a pre-trained, I used As a pre-train, I used model trained by Facebook in semi-weekly supervised fashion on Instagram and ImageNet. This is one of the best pre-training ways that we can find for ResNext. So I'm hoping that using this good pre-train, we will get the good results on our dataset. Additionally, I added an FPN to better predict small objects from my dataset. And I am using guided anchoring RPN because I simply don't want to hard code all the anchors. And I'm using a Cascade, and as far as I'm using Cascade RCNN, I am adding a cascade of 3 RCNN heads, for which I will pull features using ROI align, which pull my arbitrary sized ROIs into 7x7 region grid. And then I simply will classify this region using 2 fully connected network. After that, we will define training config, which describes how I want to match all my predictions and the ground truth, and how I want to sample of my sample ROIs from all the pool of ROIs available for RPN and RCNN. I am simply using the default parameters for all the stuffs which provided in the detection library. And the last interesting part in here is testing config, which describes how many ROIs I want to evaluate during testing phase, and which NMS algorithm I want to use during testing phase. Here I am using a standard NMS algorithm, but you also can try to play with this and change NMS to soft NMS and see what will happen. So I want to train my network on Coco dataset. So I'm simply selecting Coco dataset type, and I'm simply putting the weight to the data on my hard drive. Then I am defining loading of train and test data. And the interesting part here is only this one, is about how I want to resize my image and at which resolution I want to train my neural network. So I'm specifying that I want to train my network on the images which randomly sampled from the range of where the shorter size is lying between 400 and 800, and the bigger side of my image is not bigger than 1333. And during resizing, I want to preserve aspect ratios of my origin images. During testing, I simply want to test on a single scale image. So I use the biggest scale that I used during the training to test all of my images. Then we're defining the data loader. And the interesting part in data loader is these 2 parameters. First one is describe the numbers of images that put on one GPU. In my case, my GPU with 8 GB of RAM can process only one image at once. So I am putting batch size as 1. And I am simply putting the numbers of workers that will be loading images into the memory of my GPU as one as well. Then we want to configure our optimizer parameters. And here's the most interesting thing that most of the newbies are skipping. So as far as I'm training my backbone using a batch size of 1 image per GPU, and I'm training on 3 GPUs at once, the effective size of my training batch size is 3. And the default learning rate, which used in detection, is set for batch size of 16. And hence, we need to adjust this high learning rate using simple linear scaling rule to be the same size as the fraction of my batch size comparing to the batch size used for this learning rate. And the last part, we're simply defining all loggers hooks. We may simply use text logger hook or even add a TensorBoard logger hook if we want to visualize some training data from our training. And we defining the workdir where all of checkpoints will be saved and all of the intermediate data that produced by detection during training phase will be stored. As you can see, this is a pretty big config, and it contains a lot of stuff which may be pretty hard for newbies. So in detection 2.0, they introduced pretty good approach for defining configs like this one. As we can see, this config is much smaller compared to mine, and the trick is here. They are simply using some base config for reusing parameters from this base config and simply overriding them using this value from this new config. So by doing so, we can reuse our existing configs to fastly iterate between different ideas and to control only the parameters that are really important for our models. But I don't like such approaches because I want to open a config and I want to understand all the parameters that I used to train this model, and then to try to reproduce all the results using this full config. Now we obviously may try to train our object detector using this config, but I will not do so because the training even such simple model on 3 GPUs will take approximately 3 days. So I will omit this part, but if you are interested in training your own object detection model, you may look into the README and find getting started topic. And in the getting started, it is pretty straightforward step-by-step instruction how you can start training your own model, which are simply executing this one line of bash code. Cool. And we are done with coding time. And let's move on to detecting let's move on to detecting objects not only on a single images, but detecting objects on a sequence of video frames. And generally when we're talking about detecting objects on videos, I mean the task when we not only detecting objects, but we also tracking their histories through the time, and using this so-called object's trajectory to process them in some underlying application. So there is a lot of approaches for video object detections, but there is still no exist any classification for these approaches. So I developed my classification, which is obviously not the best one, but I like to divide all the approaches for video object detection into these three groups. First group I called non-temporal, and this is the simplest approaches for processing objects on the videos, and these approaches are assuming that there is no dependencies between the frames between the video frames, and we can simply process each frame by our one frame detector one by one, and then use some data association algorithm to build to join all these detections from different frames and form final trajectories of our objects. So these approaches are generally lightweight and they can achieve good results in video object detection, but they are heavily relying on the performance of underlying object detector. And if object detector is failing, then the whole system is failing. So on the other hand, there is temporal approaches that heavily utilized the temporal nature of the videos. So they use neighboring frames from the videos and try to incorporate this information using 3D convolutions or conv-LSTM to enhance predictions from our single frame, and hence make our object detection model more robust to different kinds of noises that come up to us from the video object detection. So as you all understand, using of 2D convolutions and conv-LSTMs, this is a pretty heavy operations. They are requiring a huge amount of computation and have a big memory footprint. So this is approaches generally used only for research purposes, and they are pretty spread among researchers, but you almost cannot find real applications that incorporating these approaches. And the last group is optical flow enhanced one. This is some approaches which stand somewhere in between non-temporal and temporal approaches. They still relying on the one frame object detectors as non-temporal one approaches, but they also using an optical flow neural networks to aggregate information about the nearest frames on the video, and trying to inject this information into our one frame detector to make it more robust to some of the noises from the video. So these approaches are generally better compared to the non-temporal one, and they have pretty similar speed, because calculating of optical flow nowadays is done by a small, low resolution convolutional neural network, which have small computational budget. So I hope that in the nearest future we will find more and more applications that using these approaches for video object detection. But nowadays, generally, commercial applications are using non-temporal approaches because they have a small computational budget and can be run almost and no cost. So let's review some of the non-temporal approaches that are widely used in the research community. So we'll start with SORT algorithm, which stands for Simple Online and Real-Time Tracking Algorithm. It's quite straightforward, and almost everyone that tried to worked with video object detection come up with such algorithm. It works in following way. Assume that we have some trajectories of some objects up to frame t-1, and we want to prolong this history of object trajectories to frame t. So we are simply applying our object detector to frame t, and we are detecting all the objects on this image. Then we are using Kalman filter and the history of how trajectory of the objects change through the time. We are calculating velocity of this object and trying to project its possible location on the frame t. And then simply using IU matching algorithm, we are trying to match predictions produced by our object detector with these projected bounding boxes, and in such way prolonging the object trajectory history. Obviously, our detector is obviously object detectors are not the silver bullets, so they sometimes cannot detect some objects. So we need to incorporate this into our pipeline. So even if we do not match our historical trajectory with some bounding box on the frame t, it is totally okay. And we simply continue to repeat this procedure for the next, I don't know, 15 or 30 frames. This is configurable parameter. And after a long time, when we cannot match our projected bounding box to any predicted bounding boxes, we are considering about simply closing this trajectory, because we obviously lost this object, and we don't want to compute some additional trajectories that mostly will be closed for the last of their lifespan. So also there is a problem of new bounding boxes that we cannot match to any historical one. So we simply considering them as new objects that simply appeared on the scene, and we open for these objects new trajectories, and we will repeat all this procedure for the whole video. This simple but effective approach won the second place on the multiple object tracking challenge in 2016, and showed almost the similar performance as the algorithm which won the first place on this competition, while this SORT algorithm could be executed on any hardware almost at real time. And during the competition, this algorithm showed 260 Hz of performance, comparing to 15 Hz of the winner of the competition. So this is simple low computational algorithm which could pretty good track all of our detections through the video pretty well, but it has one major drawback, and this is handling of occluded boxes. Suppose that the objects that we are tracking will be occluded by some other object, or I don't know, some background for a considerable amount of time. Then using our pipeline, we simply decided that we lost our object, and we simply close this trajectory, but at the same at some time point, this object will appear again. And for us, as for humans, it is obviously that this appeared object and this closed trajectory is the same objects, so we can simply match them. But sort algorithm cannot do this. And lately was introduced deep sort algorithm, which handles this problem using deep features generated by embedders to simply match not only by the relative locations of the objects, but also using some deep learning RAID approaches, and hence improving the performance of overall system. Introducing of additional neural network, which will compute for us embeddings for tracking objects, it's not the best idea, and this may be not suitable for some of applications. So recently was developed a new approach which incorporated deep sort into RCNN. And this approach calling as tracking RCNN. And it's based on the following idea. We already computing deep features in our RCNN to predict location and scores of our classes. So we can simply reuse these features cropped by Roy-Align algorithm to predict embeddings. And we then may match our embeddings from the current frame and compare them to the embeddings from previous frames using cosine distance, and simply adding relative locations of bounded boxes and their scores. We may come up with a system that learn how to match our object trajectories in end-to-end fashion. So that's all for today. But before we move on to Q&A session, let's recap the key points of this lection. First of all, object detection is one of the most interesting computer vision tasks with a lot of challenges and a lot of solutions for these challenges. Object detection is a key part of many sophisticated systems. So simply by improving performance of object detectors, we will make lives of millions of people all over the world much better. Keep in mind that object detection models are multi-component systems, so we need to try to play with their components to get best speed accuracy trade-offs that suits for our needs. Also, object detection has a lot of routines, so do not hesitate to base your object detection research on popular open source libraries, and also try to contribute some of your ideas to these libraries. I'm extremely happy that more and more researchers in object detection field are basing their research on detection, and after that they simply merge their research code into detection ecosystem. So this this helps other researchers to quickly verify their ideas, to keep quickly checked new approaches, which basically cultivates good culture in object detection and increase reproducibility of new publications, which we are often lacking in some other computer vision domains. And always try to iterate from simple ideas to complex one. It is often that some simple ideas can produce an extremely good performance at moderate or low cost. So try to play with models of different complex and to choose the best one which suits for your needs. Thank you for joining us today, and thank you for your attention. And we are ready to move to Q&A session. Okay. So the question, do you use F1 scoring for object detection? Well, basically, you can try to use F1 score for object detection, but here's a small problem. F1 score metric is calculated for fixed precision and recall. So you need to fix confidence of your detection and at some level to calculate the precision and recall at some point, and then use this value to calculate F1 scoring metric, which not the best idea. And also, I personally don't like F1 scoring metric because it is not obvious for researchers which F1 scores means. Let me try to explain this. When you're calculating F1 score is simply harmonic mean of precision and recall. And when you are seeing F1 score of 0.01, you do not simply understand what's happened with your model. Is it you have low precision, or you have low recall, or all this stuff simultaneously? So generally, F1 score do not used in object detection, and I personally do not recommend to use it for any needs. Simply use precision recall curves or ROC curves. It is much more convenient, and it is easier to understand what really happens in your system. Why do we have 2K scores for the classification layer in the faster RCNN? Good question. Let's move on to faster RCNN. So here's we're predicting 2K scores for predicting whatever this sliding window is containing some object or not. And this 2K scores corresponding to two classes. First class is foreground and second class is background. So in RPN, instead of predicting one value, the probability of that this region containing some object, we simply predicting two scores. First one is the probability that this object, this region is containing some background, and the second one, which is the probability that this region are containing some objects. So instead of doing sigmoid classification in RPN, we simply do softmax classification. But generally, you can obviously do this with simple one sigmoid score. Maybe I'm a newbie, but what are anchors in DL? Can you specify this question, because I do not understand what specifically do you want to hear for this question. Okay, which library, PyTorch or TensorFlow, has more potential in object detection areas, and at this moment, which of them is more popular in production commercial projects? Good question. So, as I already said, we have today we simply selecting from two libraries, between two libraries, between TensorFlow and detection. And if I will start a new project, I will definitely start using detection because it already containing a lot of pre-implemented stuff that I do not need to implement by myself, and I can simply concentrate on the things that really matters. But PyTorch is considerable among researchers as more research framework because it has because it is much more computational heavy compared to TensorFlow. And generally for commercial applications used TensorFlow because it can be simply optimized using the toolset of TensorFlow. And you may transform the graph in such ways that you will increase the performance of object detection model by 2 times, or even if you, or even you can try to use some more hardware specific libraries like Intel OpenMINO to optimize your object detection models from TensorFlow object detection API, which may increase the performance of your models in several times, like 3 or even 5 times faster compared even to the models which are based on TensorFlow. But detection is rapidly growing, and it already have support of ONNX. So you may try to convert some models from detection to ONNX, and then try to use to optimize them using the same OpenMINO. So I assume if you are trying some vanilla object detectors like faster RCNN or SSD, there is maybe no difference between these two libraries, and you can freely use detection because it already has a huge code base, and it is much easier to use this code base for your needs. Could you share the presentation slides and notebook to try? Sure, I will share the presentation slides and the code that I have written after the lecture. And I will, and if you do not understand some things, you can freely Slack me in our Slack, or you can simply reach me in Facebook or any other social medias or social networks, and you you can simply reach me anywhere, and I will help you to understand some parts that you do not understand during this lecture. Okay, the L is deep learning. Why approaches would you advise to use for RCR algorithms? Okay, this is different questions. So let's try the older one. Maybe I'm newbie, but what are anchors in deep learning? I still do not understand this question seriously. I'm extremely sorry, but if you can try to put this question a little bit different, then I will try to answer it in a proper way. in which what approaches would you advise to use for RCR algorithm? Okay, I will explain what is OCR is algorithms for transforming letters and digits that's written into text. And the first step in OCR algorithm is simply detecting the text on the image. And this image obviously can be arbitrary size. It can have arbitrary shapes. So it is pretty tricky to predefine all the anchors to properly cover all the stuff. So I will definitely recommend to use some anchor-free approaches like CornerNet or trying guided anchoring in your faster RCNN model or in SSD to properly cover all this distribution and simply try to detect these regions. And I think that it will be enough to get the good detectors for detecting text, and then you can simply crop this text and put into open source OCR systems. I honestly not familiar with OCR, with popular OCR libraries, so you can try to Google it and to find open source OCR algorithms, or even try, as far as I know, Amazon and Google has services for performing OCR for customers. How to win Kaggle in how to win on Kaggle in object detection competition? Well, this is a tricky question, but some of the obvious way to do so, you simply incorporate all of these ideas into a single network, like Cascade RCNN, like guided anchoring, deformable convolutions, focal loss, FPN, Roy Align, SoftNMS, etc. And you are simply get a bunch of highly computational GPUs. Perfectly, it will be a new DGX with the new generation of Tesla cards, and trying to fit the best model which you can fit. And you're training this model for maybe several months. And that's it. You will get state-of-the-art algorithm on on Open Images dataset. What does the term anchor means? Also, what is the difference between anchor-based and anchor-free approaches? Thank you. Okay. As I already said, anchors, it's simply the name of such predefined bounding boxes, shapes, and sizes, which we are using to slide over the feature map. I honestly do not know why they named these boxes as anchor boxes. And if you know why they're using such names, so please chat me in the Slack or simply answer about this into our Q&A session channel. Okay, what is the difference between anchor-based and anchor-free approaches? So the basic difference is that anchor-based approaches are trying to simplify the task of classifying, of detecting possible regions where located our objects by simply predefining a set of bounding boxes. And we are simply trying to detect whatever inside of these bounded boxes are containing some object, and we simply use features to classify and to adjust these anchors to well cover all the distribution of bounded boxes in our data set. And the anchor-free approaches is the opposite one. They are trying to get rid from these anchor boxes, and they are trying to predict the shape of our box directly from the image without any prior assumption about boxes, shapes, and scales. So theoretically, anchor-free approaches are more robust to input distributions and can easily transfer from one bounded box, one distribution of bounded boxes to another without any drops in the performance. But for today, this is active area of research. So these approaches are mostly in the research area, and mostly researchers are interested in using and improving these approaches for publication. And we cannot use these anchor-free approaches for our commercial applications because they are requiring deep features that can be get only from high computational deep neural networks like Hourglass 104. So generally, you can try to play with these anchor-free approaches, but it is definitely not the best way to do some to create some commercial applications. SSD network versus YOLO v3 v4. Oh, this is hot topic. So, at my opinion, there is almost no difference between SSD and YOLO v4, and now I will explain this. So, simply SSD is idea that we are directly predicting locations and classes of our objects from the feature maps that calculated by our deep convolutional neural network and simply concatenating them. So YOLO is performing object detection using pretty similar idea, but in YOLO, we can see that some minor differences in implementing this algorithm. So instead of using some networks, some classical networks like VGG16 or ResNet 50, in YOLO v3 v4 incorporated DarkNet 53, which simply modified version of ResNet, and this modified version of ResNet contain some operations that are not well optimized on modern hardware. So in theory, DarkNet 53 is much faster compared to ResNet 50, but in practice, when we are trying to execute ResNet 50 and DarkNet 53 side by side on some underlying hardware, we can see that ResNet 50 almost always faster than the DarkNet 53. Plus, YOLO trying to learn different targets in coordinates branch. So instead of learning regression for the corners, that they are learning regression for the center of the anchor box and the height and delta for the height and width of our bounded box. So we're simply putting regression task in different terms, but simply under the hood, YOLO v3 and v4 is simply modified SSD. What are the optimal input size, image size, and the byte size while training? How to choose them? Well, this is a good question, and it is pretty hard to answer to this question, but common logic is following. The input image size is depending on the task that we are trying to solve. So if you want to detect small objects, smaller than 32 by 32 pixels, obviously you want to try to run your detector on high resolution images where our objects can be easily distinguished from the background and easily classified. So the smaller objects you want to detect, the bigger the image size you need to feed into your network. But there is also some small dependence between input image size and one stage and two stage approaches. Generally, input resolution for one stage detectors are much smaller compared to two stage detectors, because this simply depends on the underlying ideas that incorporated in these detectors. First of all, SSD requires much smaller input image, because they are predicting objects using different feature maps from different stages of the network, and hence they are trying to incorporate different RPNs for different stages, and by doing so they can predict pretty small objects on the early stages of the network, and pretty big one on the using high resolution feature maps from our network. On the other hand, when we are trying to predict objects using our two-stage detectors, we are using following feature map, and hence we want that this feature map was as big as possible to try to apply different because we want to apply a higher number of these anchors. And so by doing that, we will cover much more objects, and we will definitely cover them with higher accuracy, and hence the results will be better. So generally, two-stage detectors are more preferable for high resolution inputs, and if you cannot afford to compute high resolution image by to process your high resolution image by convolutional neural network, it is definitely the best choice to choose one stage detectors. And the byte size while training. So also byte size is a hot topic in object detection because, as you remembered from my practice session, I tried to train my RegSNeXt 101 based Cascade RCNN, and using input resolution of 1336 by 800, this to process this image by on GPU, you need to have at least 8 GB of RAM to process only one of image. So if you want to extend this number to 2 images, you require 16 GB of RAM. And if you want to process 4 images, you already required 32 GB of RAM, which is high end, which require high-end GPUs like Tesla V100 or Tesla A100, which generally not affordable for say, common researcher. So generally, we are using batch size of 1 per GPU for two-stage detectors because we, we can fit only one image into our memory. And when we are switching to one-stage detectors, it is which have smaller input resolution, which have generally shallow networks. We may fit already batch size of 16 or 48 images into our training batch. So the larger batch are more preferable for object detection because and this is generally more preferable for any computer vision tasks. The bigger batch you have, the more better model you can train. But for object detection is pretty critical point because if you have batch size smaller than 16 images, you cannot reliably calculate moving mean and variance for batch normalization in your neural network. And hence, if you have small batch size, you need either to froze this statistic to prevent overfitting of your model, or you need to increase batch size and switching from simply from two-stage detectors to one-stage detectors, or decreasing the input resolution into your training network. So this is looking like I'm already answered to all the questions. So do not hesitate to type down your question if you have anyone. I will definitely answer to them. And if you already asked all of your questions, I think that we may end our lecture. So organizers, what do you think? Do we wait several more minutes for participants to type their questions, or we may end lecture now?
Yeah, we can wait for questions, 5 minutes maybe.
Okay, we will wait, say, 5 more minutes for participants to write their questions, and then we will end our lecture.
Okay.
Good. So while we are waiting for new questions, I already posted the slides from our presentation for this lecture. So you can review all the cool stuff that we are reviewed today, and you may also come up with some new questions while you are watching to these slides. So we have already new question. Just CV related questions: RGB versus grayscale versus U. So this question about color space and about the difference between RGB grayscale and U color format. So we will start with comparing RGB versus grayscale. And actually for object detection, there is almost no difference between grayscale and RGB. But if you can get the RGB image, it will be more preferable because RGB image are containing much more information, and you can simply use this information to better distinguish between different complex objects. So RGB is definitely the best one. And the next question is RGB versus U. It is much more complex question, and to answer this question, I will show what is U format is. And U format is simply decomposed our RGB image into 3 different components. I actually do not remember how they named, but I remember that Y component is simply grayscaled image, which can be received from our RGB image and has the same shape as our RGB image. And we have 2 additional components which called U and Y, and they have spatial size 2 times smaller compared to Y component. And this is internal format for saving JPEG images, and actually such format contain much less information compared to RGB. So knowing that the Y and Y components are containing much less information, or not less information, but has smaller spatial size, while have the same amount of data, we can simply incorporate U format into our object detection model to simply process this low resolution Y and Y channel in a special way that will reduce the computational amount of computations that required to process the whole image. And simply by switching from RGB to U format, we may save a lot of computation for processing this image. And actually in 2018, Uber published that they are using, that they are predicting, that they are classifying and predicting object types from U images. And this is much cheaper compared to convenient way of predicting from RGB image, while maintaining the same accuracy as simply predicting from RGB. I hope I answered your question, and I'm switching to the next one. Which models or combinations of approaches are used in real-world applications in Tesla automated driving systems? Thanks. Okay. So I actually don't know what really under the hood of the Tesla Autopilot. I suppose that this information is under NDA, but on the high level, Tesla are using several cameras that's placed at different locations all over the car, and they are using these inputs from different cameras to predict different targets. Like they are predicting they are detecting some objects, and they are using detections from several cameras to calculate the distance to these objects and to define what's the type of this object. And by simply incorporating all this information, they are trying to get some insights for Tesla controller to simply understand how do we need to behave to be on the road, to preserve safety of our passengers, and to drive our Tesla car from location A to location B. This is actually my high-level understanding how Tesla Autopilot is working right now. But according to Andrei Karpathy, which is director of research in Tesla, they right now are moving from simple frame-by-frame simple frame object detection to detecting objects on a sequence of frames, and hence not only detecting 2D bounded boxes, but also detecting the deeps of the objects. It's like switching object detection from 2D to 3D, and it is much more complex task, and it is definitely require a lot of video data, a lot of computational capabilities, and by switching from 2D to 3D, we can get a lot of additional information that extremely useful for maybe extremely useful for controller to predict how to behave in the right way in some corner cases of in some complicated cases, like stopping our Tesla car in front of pedestrian, or understanding that vehicle in front of us are lowering the speed, etc. So it's all about making autopilots more safer. So we already used all of our 2 hours for election, and I don't see any new questions from our participants. So I think that we can ending up our election.